What up, everybody? A new day, a new full lesson by me, the math teacher GOAT. Today in AP Precalculus land, we're talking about section 1.4 Polynomial Functions and Rates of Change. Lots of rates of change lately, tons of them. But, you know, that is what it is. Make sure you like and subscribe. Make sure you go to the description and download the notes. We're going to get right into it. These things are about half an hour long, so buckle up. Think of how you could use rates of change to find if a function is linear or quadratic. Well, what you do is if it's linear, then the rates of change are going to be the same number every time. Now, let's see what happens. So we add 27 to get from negative 27 to 0. We add regular 7. So right now it's not linear, but we'll keep on going and see what happens. Subtract 7, right? Subtract 15. Subtract 17. What is that? Subtract 13. Subtract 3. Ooh, now we're going back. Add. What is that? 13? Yeah, you're adding 13 to that guy. Let's add. Oh, I made that big. Let's add 35. Let's add 63. Well, you're not linear. So if it's quadratic, what we're going to do is we're going to see if the same thing happens and see if we get the same number here. Rates of change of rates of change. So to get from 27 to 7, you subtract 20. To get from 7 to negative 7, you subtract 14. So once again, this one's not quadratic. Very interesting. Subtract 8. Subtract 2. Add 4. Add 10, add, what is that, 16, add 22, the Taylor Swift special, add 28. All right, well, it's not linear, and it's not quadratic. So what are we supposed to do here? Does the table represent a linear function, quadratic function, or a cubic function? So you know what? It's not like I do this for a living, but I have a feeling I know what's going to happen. If I take it one step further and do rates of change of rates of change of rates of change, I'll probably get something that's cubic. So what do you do here? You add 6, 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 add 6. So what we have here is we have something that's cubic function, because the rates of change with the rates of change with the rates of change are the same over equal input interval values. Oh, fun stuff, fun stuff. Wow, we learned something today. Well, let's sketch each graph. Listen, I'm not looking for perfection here. I'm not looking for so much accuracy. What I want to do is I want to take a look at this and realize that this is a cubic function with a positive leading coefficient. So it's going to look like this. Okay, am I right at all on my axes? Probably not, but that's not the goal here. What I have right here is a quartic function, okay, and it's positive leading coefficient, so it's going to look more like a W, give or take. So this has a bump and opens up left and goes to the right up. So this goes up left, up right. So the limits are different here. What do we have here? We have ourselves a quintic, so that's going to bump, 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 bump up. And since that's a positive leading coefficient, it starts from the bottom, like someone that we should not name, and ends up here, like someone we should not name. I think you know who I'm talking about. But what we have is we have a polynomial. And a polynomial is a mathematical expression. Hold on, let me write this out. A polynomial is a mathematical expression that consists of variables, also called indeterminants, and coefficients combined using only addition, subtraction, multiplication, and non-negative integer exponents. Okay, so no square roots around the x. All right, x is not allowed to be in the denominator unless it simplifies. Positive exponents attached to x. So we would say here that my leading term is 7x to the 5th, making this a quintic. My leading coefficient is a positive 7, which means it starts from the bottom. My degree is a 5. That's what makes it a quintic. Okay, so we need to know and we need to be very familiar with polynomial behaviors if we're going to keep on moving. Okay, and so again, what we saw here, let me just go back. That's not what I wanted to do. I didn't want to move things around. Ugh. All right, let's do this. So again, we know the behaviors of these things. You learned this in Algebra 2. Okay, if it's a positive leading coefficient, it always starts from the bottom if it's odd. It starts from the top if it's even. And, it has similar behaviors depending on the odd or even degree. Okay, now when you throw negatives in front of all of these, things flip upside down literally, and the end behavior is opposite. Okay, so knowing that, knowing stuff about end behavior, and if you don't know about end behavior, maybe pause this video right now and just watch a video on polynomial end behavior, and that'll probably give you a better idea of what we're doing here. If a polynomial switches from increasing to decreasing, there will be a local, or some books call it relative, maximum input value. Okay, again, what it's saying is you have this function goes from increasing and then all of a sudden it's decreasing. You're going to have a maximum. Does that mean it's the absolute maximum or the most important maximum? No, not at all. Okay, this is just a maximum area. Keep in mind, that guy could shoot up and go like that at some point. So that's not the greatest number there, not that we know of. If a polynomial switches from decreasing to increasing, there will be a local or a relative minimum output value. So here we are, decreasing switches to increasing, and there's our local. Okay. I might be jumping the gun here and might be getting ahead of myself, but I used words like absolute. Okay, absolute is the tallest number or the smallest number that you have in a graph. These aren't indicating that this is the tallest or the smallest. It's just like a bump or a hilltop. That's all it is. Okay, so keep that in mind as we do some of these problems. Now, if we have endpoints that are included, okay, you're allowed to call that local as well. Okay, it doesn't mean it's absolute. It doesn't mean it's the smallest thing. Like I would look at this graph, okay, and if I were to ask to label this graph, I would call you right there a local minimum. I'll abbreviate it to local min. I would call that point right there a local maximum, which I'll abbreviate to local max. And here we have another endpoint, and nothing goes below that. That there would also be a local minimum, which I'll abbreviate as local min. Okay? Now we are going to talk about the global and the absolute maximum or minimum. These are the numbers where you can't go any higher than it. Now, if they're, well, I guess I don't want to jump the gun either, but let's just look at it. Let's just look at this picture right here and we'll label a few things. Okay, now let's take a look at the local and the absolute. An absolute maximum or an absolute minimum means you can't go higher or lower than that. A local can also be absolute. Okay, so that can have two names. So if I'm going from the left and to the right, we just learned up here that if there's an endpoint, it's considered a local minimum. But since there's no place lower on the graph than that, that would also become the absolute or the global minimum. The abs min, as I'd like to call it. Abs, because I have 6 of them. Now, as we move to the right, we have this bump up here. We go from increasing to decreasing. So that's a local maximum. It's not the absolute maximum because we're going to go higher than that. Then we keep going, we hit a bottom, and then work our way back up. So we go from decreasing to increasing. That's a local min, not an absolute. We're going to increase and then decrease. So here's another local maximum. We're going to go down here, decrease to increase. So here's another local minimum. And then all of a sudden we keep going forever. So if you're thinking, absolute maximum. No, you're wrong. This indicates that we are going to keep on going. So there is no absolute maximum. Not at all. So let's answer some of these questions. We have an absolute min of what when x equals what? Well, here's our absolute min. So we have an absolute min of -2 when x equals -6. We have we have, we have a loops. We have an absolute max of what when x equals what? Well, we don't have one. It doesn't exist. Doesn't exist at all. Now we have several relative mins, so let's name them all. We have one when x equals from left to right -6, -3, what else? 2, and that looks like that's that. We have two relative or local maxes, and those happen at -4 and +1. You know, the pain in the butt about these problems is having to switch between words like local and relative and having to switch between absolute and global. It all depends on your teacher. I know when I teach calculus, I call them absolute maxes. I've always done that. I don't know why. That's the way I was taught it. That's the way I did it. So, and I don't call them global when I teach AP Pre-Calc. I guess I'm supposed to, but I just don't think about it. You know, same thing with the other words that we could use. So, is what it is what it is. Let's learn a few more things, shall we? All right. Now, a zero is wherever you have a graph that hits the x-axis. Common sense would tell us that at the worst, I have this little shallow hill right here. Or I could have this really shallow pool type thing. At the very least, if you have zeros, at least 2 zeros of a polynomial, you will have at least one local extrema. So we will write out if you have 2 zeros of a polynomial, okay, there must be at least one local extremum between the two numbers. Extremum is just fancy word for either maximum or minimum. I don't know if I mentioned that yet, or I don't know if you've heard that before, but you will have either a minimum or a maximum, and you could have more for all we know. So that leads us to weird problems like this guy right here. Let f be a polynomial function with values f of -2 is 0, f of 0 is 5, f of 4 is 0, and f of 7 is -1. So if I were to draw just a very basic coordinate plane, okay, at f of -2, we have a 0. At f of 0, we're up here at 5. I know it's not drawn to scale. That's not the point. At f of 4, we're at 0. And at f of 7, we're at -1. So we'll put 4 there, we'll put 7 here, and we're at -1 here. Okay? Now, we don't know what this picture looks like. We don't know what this picture looks like. We know that at the very least, like this could be like, at the very least, what we know is in between -2 and 4, in between -2 and 4, there's going to be a guaranteed maximum, a local maximum, okay? So we will say on the interval, -2 to 4, there exists a local maximum. We just don't know what everything else looks like. I mean, this could have been a nice smooth picture, but at the very least, we know that there's going to be a local maximum. Now, what you know from before about the end behavior of polynomials, if there's an even degree, it's going to start one way and end the same way. Okay, it doesn't matter how many dips there are, it's going to start way and end one way and end the same exact way. Okay, so we are guaranteed an absolute extrema somewhere. This is a leading positive coefficient, and it's going to hit a bottom somewhere. Similarly, this is a negative leading coefficient, and that's going to max out somewhere. So a positive leading coefficient, which starts at the top and ends at the top, you will definitely have an absolute minimum, no matter what. Okay, this is a positive leading coefficient. A negative leading coefficient is going to start from the bottom and end at the bottom, and if that's the case, you're going to definitely have an absolute maximum no matter what. All right, so let's just sketch these out anyway because I think it's good that we see them in front of us, and state if there's absolutely an absolute maximum, an absolute minimum, or neither, or whatever. So what do we have? We have ourselves, our top degree is for positive leading coefficient. Okay, so this is going to start at the top, bump, 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 okay, and end at the top. So we are guaranteed an absolute minimum. This guy is a negative degree of 6. So this is going to start from the bottom, bump, 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 and hit down there. So we are guaranteed an absolute maximum. This has a leading coefficient of 3. It's positive. So I'm sorry, a leading coefficient of 6, which is positive, my bad. It's a degree of 3, which means it starts from the bottom and ends up here, like a rapper who should not be named. So are we guaranteed an absolute maximum? No. Are we guaranteed an absolute minimum? No. There won't be any. There'll be a neither. All right, so just in case you forgot, we talked about this before. An inflection point, because we're going to answer a bunch of questions, an inflection point is going to be part of it, is where you change concavity. So right here we're concave up, and then all of a sudden right there at that random spot we hit concave down. An inflection point is where you change concavity. So based on that information, let's finish this guy out by answering a bunch of questions, and we can finish this section right here. So a bunch of them, a bunch of them, a bunch of them, a bunch of them. All right, so we have ourselves this weird looking thing. We're talking about absolute maximums, absolute minimums, relatives, blah, 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 blah. So let's take a look at what we have. We have ourselves an endpoint, which means we have a local, since this is at the tippy top, a local max. This, however, is not an absolute max because it appears you are going to be just that. So we'll go over here and say you're an absolute max. But it's also a local max as well because it hits the top. All right, but going back from left to right, local max, decreasing to increasing local min. Not the absolute min, because we can see that it keeps going down. Then we're increasing, hits here, starts decreasing. So this is a local max, but since this y value is higher than all of the others, it's also the absolute max. Then we keep on decreasing forever, and since this will continue going down forever, there's no local minimum here, and there's no absolute minimum here. So we have an absolute minimum of nothing. We have an absolute max of 2 when x is 1. Okay, when x is 1, absolute max is 2. We have relative minimums at just one spot, and that's at -1. And we have relative, also known as local, maximums at 2 spots at when x is -4 and when x is +1. All right, all right, all right. Okay. For the polynomial function h, the rate of change of h is increasing for x is less than 3 and decreasing for x is greater than 3. Now let's be careful. Let's be careful of what rate of change is increasing means. Rate of change is increasing is not an increasing function. Rate of change is increasing indicates concave up, where your slope is going up. Then also right here at 3, it's concave up. Then all of a sudden at 3, it starts decreasing, which means we hit an inflection point, and now we're concave down. Okay, so that's what's happening here. Okay, at x equals 3, why did I put 3 again? When x is 3, we hit this inflection point. So, what does this mean? Which of the following must be true? The graph of h has a minimum at x equals 3? Nope. The graph of h has a maximum at x equals 3? Nope. The graph of h has an inflection point at x equals 3? Yes. Is concave down at x is less than 3? Nope. And concave up at x is greater than 3? Nope. D's got to be my answer because the graph of h has an inflection point at 3. There you is. Concave up for x is less than 3, there you is. And concave down for x is greater than 3, there you is. The answer is 3, there you is, there you is, there you is. Where did that come from? Oh, the other part of x. I'm a mess today. Because, you know, I'm never a mess any other day. Let's do more. The polynomial function g is given by g of x equals x minus 5 in parentheses and 4x minus 2 squared. Which of the following descriptions of g is true? All right, so you're going to see this a lot in future problems, okay, specifically when it comes to rational functions. But I only care about the polynomial's degree, and I only care about the leading coefficient. So this is a little trick. If you're given something that's factored, okay, the way you find the leading coefficient is you take the leading coefficient of each one, of each factor. So you have an x right here, and then you take however many you're supposed to take for this one. Okay, since the multiplicity is 2, we're going to write that out twice. So if we were to FOIL all this out, that would take a while. Or all we care about is the leading coefficient. So take the leading coefficient of each factor and write it out as many times as the exponent tells you to. I have x. I'm going to multiply 4x to that, and 4x again because of the multiplicity being 2. X times 4x is 16, x to the third. So g has a polynomial of degree 2? Nope. G has a polynomial of degree 2? Nope. G has a polynomial of degree 3? Yep, with the leading coefficient of 4? Nope. G has a polynomial of degree 3? Yep, with a leading coefficient of 16. Yep. We are going to do this a lot. Get used to that. Get used to that. Get used to it. You're going to see it a lot. All right. Values of the polynomial function g for selected values of x are given in this table. If all of the zeros of the function g are given in the table, which of the following must be true? So all of the zeros are given. So you're a 0 and you're a 0. Okay, so labeling the few points that we can without worrying about these huge numbers, we have a -2, we have a 2, we have a 4, we have a 6, we have an 8. Sorry about that, everybody. Okay, at -2, you're way down here. At 2, you're at 0. At 4, you're at 5. At 6, you're at 0. And 8, you're at 20. Huh. So what's happening here is, I don't know exactly what it looks like, but all the zeros are labeled. So this is going to, at some point, ricochet off the x-axis. Wow, did I miss that dot? Hey. Nope, nope. Can I move the dot? Can I move the dot? No, it won't let me. I give up. Just pretend it goes through the dot. Use your imagination. All right, so what I have and what I'm guaranteed is we have a local maximum somewhere here. I don't know where, but what I'm absolutely guaranteed, though, is a local minimum at 6, 0. Since there are only 2 zeros, and they're giving us this one here at 2 and this one here at 6, okay? I don't know. Like, again, I don't know if I have these dots here, right? Because this is kind of what we're looking at. This could look like this. And then come back down and ricochet up. Okay, so I don't know if you're a local max. But what I do know is you can't go any lower than that, because if you did, you'd cross the x-axis and have to cross the x-axis again to come back up here. So you are absolutely a local minimum. So what I'm guaranteed is this function has a local minimum of 6, 0. Okay, bizarre question, bizarre problem, fun though. Speaking of fun, last problem. The polynomial function h is given by this horrible mess, but what I see is it's quintic, and determining on what p is, it just says p is not 0. Q, R, S, and T are constants, all right? Which of the following about h is true? Now it says p is not, so, all right. We don't know what any of these numbers are. We just see that this is something to the 5th power and it's not 0. So it could be 15, it could be -12, it could be 1, I don't know. It's just not 0, okay? So what we're guaranteed is a picture that's going to look something like this. Or, so we're not guaranteed any absolute anything. Okay. Now they're using the word global. So what we do know is there's no global anything. Why? Because it goes down forever, it goes up forever, or it goes up forever, it goes down forever. No global anything. So it has both a global maximum and a global minimum? No. It has either a global maximum or a global minimum, but not both? No. It has neither a global maximum nor a global minimum? Yep. And the nature of the global maximum or global minimum for H cannot be determined without more information about Q, R, S, and T. No, dude, you could all be zeros. You could all be zeros. It doesn't really matter. And if they were zeros and if you were one, then you would have this weird thing that would look like this. It would look like that. But either way, it's going to start from the bottom and end up here. Ugh, I hate quoting that because it sounds like a guy that we're not allowed to talk about anymore. But either way, these guys don't matter. The only thing that matters is this. And since P is unknown, and since we do know that this is 2 to the 5th, it's not going to be an even thing, which means you're not guaranteed a global or absolute anything. What you are guaranteed, though, is a solid education thanks to yours truly. And since I gave you a solid education, make sure you do a couple things. Hit that like and subscribe button, okay? A lot of my people who watch my videos don't subscribe, and it goes a real long way for me. It makes me look good, and I'm trying to build a brand here. And what you really should do is, watch my random AP Precalculus videos. So, like, the way you would do that is you would just type out Math Teacher Goat, AP Precalculus 1.4, and it'll just give you a couple more examples that you could use to help you understand things a little bit better. But on that note, thanks for watching. I appreciate you guys. The next one's going to be 1.5. I hope you have a good day. Love you. Bye.